What's up, guys? Mrs. Thompson here, and today we're covering chemical equilibrium. And on here we have a picture of the Leaning Tower of Pisa. Why? Well, somehow this building has maintained balance even though it's leaning. So when we think about chemical equilibrium, we kind of think about a balance that's going on. Okay, when we first talked about chemical reactions, we were just talking about reactions that go to completion, or we assume that they go to completion, that the reactants, as soon as they react, will turn into products, just like this. Reactants change into products. Things that can do this are things like fireworks, burning wood, things that aren't very, what we call reversible. They won't actually go back into making something else or making the reactants easily. So I mentioned that word reversible. What is a reversible reaction? It's real simple. It's just after the reactants become products, can it easily go back from products forming into reactants? And there actually are a lot of reactions that can do this. And what you would see when you are looking at a reversible reaction, how do you tell that it's reversible, is it has a double arrow. So it has two ends to the arrow, just like this arrow right here is going in the forward direction, and this one's going in the reverse direction. So you might see it look like this. You might see it look like that, which is what I have up there. And then you could see two half arrows, like that. All right. Phase changes are also reversible, meaning I can take something like ice and melt it into liquid water, and then that liquid water can easily freeze back into solid ice. So phase changes are definitely an example of something that is a reversible, not reaction, but a reversible process. And so the example here is water, solid, ice, turning into liquid water can go back. And then remember, to do that, all we have to do is change the amount of energy by increasing it or decreasing it in that way. Okay, now let's talk about another word that you need to know, and that is dynamic equilibrium. I guess that's two words. It's equilibrium that you need to know. In a reversible reaction, as the reactants form products and the reverse reaction begins to occur, what ends up happening is eventually the forward and the reverse reactions will proceed at the very same rate. We call that equilibrium. Okay, so here's a diagram that helps to show that. Okay, so here I am. Here's the rate over time. Here's the forward rate up here. Here's the reverse rate. And eventually they are equal. Remember, the rate is how fast those reactions are happening. So the forward reaction rate eventually equals the reverse reaction rate. It's not that they equal in the amounts, it's just that they're equal in how fast they're moving. Okay, so if we look at this diagram here, it shows how the reactants change over time. So they're decreasing, and then they kind of steady off as the reverse rate and the forward rate are equal. And then for the products, they go up, and then they are about even. Notice that these two amounts are not the same. So do not think that equilibrium means it's the amounts that are the same. It's how fast they're moving that's the same. All right. This is called dynamic equilibrium because both reactions are still happening. They have not stopped. Okay, they do not stop. An equilibrium has been reached. So at equilibrium, the concentration of the products and the concentration of the reactants do not change. The specific molecules within them are changing, but the amounts aren't changing because their rate has equaled out. One analogy to this is if I took a bucket with water and I have a faucet that is pouring into the bucket and a faucet or spigot that's coming out of the bucket. Okay, if this is pouring in at the same rate that this is pouring out, what's going to happen to the amount of water that is inside the bucket. Well, as long as what is being let go is replaced here at the same amount, at the same rate, then nothing's going to happen to the amount of water in the bucket. A dynamic equilibrium has been met. Now, the specific molecules within it have changed, but the total amount inside the bucket has not. You can demonstrate this using beakers of water. Okay, she keeps pouring in. Now. Okay, so number 5 here, when we reach dynamic equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. This does not mean that the concentration of the reactants and products are equal, just that they have stabilized and they are the same constantly. Not the same with each other, but the same on their own. Okay. The equilibrium constant, KEQ, is a ratio of the products to reactants at equilibrium. We have to know how to make an equilibrium constant, and it's really not hard. You can make this easily. Just don't forget how to do it. KEQ is products over reactants. So the K just stands for constant, EQ just stands for at equilibrium, and then these little brackets here just mean concentration in terms of molarity. And then what we do with this is we take the coefficients and we change them into exponents. So I'll show you what that looks like. You need to know that solids and pure liquids are completely left out of an equilibrium expression because they are pure. They do not have a concentration. So you can't put them into concentration brackets because they're pure. We can do this with gases and things that are aqueous. All right, so what we're going to do with that equilibrium expression is we're actually going to calculate an equilibrium constant. And so we'll get a value or a number that we can use. And that number can tell us a few things. One is if the reaction is more product favored or reactant favored. And so if the value of KEQ is greater than 1, that means that there are more products on the top of that expression. The values on the top are greater than the values on the bottom. And so it would be product favored. This would make a lot of products and just a little bit of reactants. It would actually not go in the reverse direction too much. If the opposite were true and the KEQ value was very small, less than 1, not negative numbers, these are all positive. What I'm referring to are things like 0.005 or 1.5 times 10 to the negative 5 or negative 25. These are really, really small values, and that just means that the products are more favored than the reactants are. One thing you need to add is that KEQ values, the numbers that we get from calculating these, change if the temperature changes. So KEQ values are only good at one specific temperature. As soon as that temperature changes, we need a new KEQ value. All right, so we're going to write the expression for this reaction right here. It's a reversible reaction. You can only write these expressions for things that are reversible. Okay, and we know it's reversible because of the double-headed arrow. All right, so here we go. KEQ is equal to products over reactants, and we're going to separate each one of the products with brackets. We're going to take the coefficients and make them exponents. So H2 goes into brackets. The 2 that is in front of the H2 becomes the exponent. All right, we can tell that this is separate from this. It goes in its own separate bracket because it's separated by a plus sign. So we're going to put the oxygen in its own brackets. And then there isn't anything in front here. It's not a 0, it's a 1. We could put an understood 1 at the top or just leave it like that. And then that's products over reactants, so we need the reactants now. And we have H2O, that is going to go in brackets, and the 2 is going to go in the top. It's going to become the exponent. Couple things. Notice that I put everything into this expression. Why? Because these all three are gases, and gases can go into the expression because they would have a concentration. Sometimes we just put them in terms of pressure instead of molarity. Okay, but either way, gases can all go into the expression. This is an equilibrium expression right here. The other thing, notice I did not put the symbol for gas inside of this expression. None of them say G next to it, so get rid of those. No, the other thing, there aren't any arrows or plus signs, so that's it for the expression. All right, second one, we're just going to write the expression for this. We're going to check to see what each one is. Gas, gas, gas. All three can go in. Remember that solids and liquids cannot, so aqueous and gas can. So here we go. We're going to put KEQ, products, HI, coefficient 2, over H2 in brackets and I2 in brackets. Neither one of those have coefficients, so this one's done. Number 3, now we have what's called a heterogeneous equilibrium. We were dealing with homogeneous equilibrium in that all three were gases. In this one, we have a combination. We have solid-solid gas. So this is a heterogeneous equilibrium. All right, so that means that some of these things are not going to be included. The solids and liquids are not. So this is not included, and this is not included. All right, so KEQ is products, which is CO2 in brackets, no coefficient, over reactants, excuse me. So since this can't be in there and this can't be in there, this is it for my expression. It's just the products, no reactants on the bottom. All right, number 4, write the equilibrium expression for this one. Another heterogeneous equilibrium. One's gas, one's liquid. So we're going to do KEQ. H2O liquid is pure. We cannot put that into the expression. Okay, so we'll leave that blank for now. And then on the bottom, we can put the H2O because it's a gas. This should look really funny to you. In the last example, we had it on the top, so it didn't look funny. But in this one, there's nothing on top, and we can't just leave that. So we have to hold the place of the pure substance. And so in order to hold the place of the pure substance, because there isn't anything on top, we just put a 1. Really what we're doing for each one of these is we are putting a 1 for each pure substance, but they're not always necessary to show. All right, so then what do you do if you have to calculate it? So calculate the KEQ, and here are the concentrations. The first thing you have to do is write the expression. So there's that. Take a moment, write the expression. All right, so then KEQ, hopefully you wrote this expression here. Great. Then you just plug in the values. These are all molarities. So we plug in the numbers. 0.33 was the amount of NH3. N2 is 0.533. And H2 is 1.6. And we plug in their exponents just as is. And we plug that into our calculator. And I got 0.399. Now you should practice doing that. If you need help with this, I can help you. You might want to put parentheses around this. If you're having trouble with the exponent parts, let me know. All right. As far as units go, this level, we're not going to worry about the units. You might move on and have to worry about units, but we're going to say that K, there's a lot going on, they're unitless. So we're done with that. The next question here is, does this equilibrium lie to the left or the right? Which this is just really saying, is this reaction reactant favored or product favored? So we're going to look at the numerical value that we got here. Okay, remember this is only valid for one temperature. In fact, in the question, sometimes they'll mention a temperature. This one does not. If they mention a temperature, don't let that throw you. That's just what their values are at that particular temperature. Okay, so this reaction it's been settled, and we measure the concentrations at which they're no longer changing. That's the equilibrium concentrations, and so we plug in the stuff into the expressions, or the concentrations into the expressions, and I got 0.399. Okay, so 0.399 is that less than 1 or greater than 1? It is definitely less than 1. Less than 1 means the equilibrium lies in the denominator. Okay? This is bigger. So the denominator, those are reactants. So this is reactant favored. K is less than 1. It's reactant favored. The equilibrium lies to the reactant side, which is the left side. It's reactant favored. All right, this one. Try this one out. Okay, let's do this one. So there is a temperature here. Remember, you don't need to do anything with the temperature. It's not part of the calculation. You simply have to say these values are only good for that temperature. Okay. So first, write the expression. Second, plug in the values to the expression. Then calculate it. And I get 0.00. Oh, we've got something less than 1 again. So if it's less than 1, which is also this in scientific notation, then, oh, I didn't write this. This is definitely reactant favored. Reactant. I'm not good at this at all. That's why I don't usually write on here. Reactant favored. Alright, hopefully that was simple enough. I will see you next time.